Here's a couple of useful definitions. The first thing I want to talk about is what a bounded sequence is. And it's easiest just to draw a picture of what a bounded sequence looks like. So I'll draw the graph of a particular sequence. And so let's say that we get points like so. And maybe it looks like it's kind of going along a sine curve. But what's important is that a sequence is bounded if you can find bounds for that sequence. Basically, you need to find two numbers, a and b, such that the sequence always stays greater than a and less than b. It could be equal to a or equal to b, sure, that's fine as well. But as long as the sequence always is between those two horizontal lines, then that's called a bounded sequence. And in fact, we call a and b its bounds. Okay, so a sequence would not be bounded if, say, it diverged off to infinity, for instance. That would be a good example. And the picture of that would be something like so. And let's suppose that we had something like, it looks like a parabola, right? Like so. As long as it's going out to up towards infinity, like in that direction, no matter what I pick to be my upper bound, my b, no matter how high I picked my b, there's something higher. If I pick this one, there's something higher up there, so on and so forth. That would be an unbounded sequence there on the right. Okay, let's take a look at some examples where we need to identify if a sequence is bounded or not. So here we have a sequence a sub n, where a sub n is equal to n plus 1 over n, and we need to know whether it's bounded or not. Okay, and in order to prove that a sequence is bounded, we just need to identify its bounds. And so here's what I can do. We can actually just write out a few terms of the sequence, and so we have to start by plugging in 1, right? So that's going to be 1 plus 1 over 1, 2 plus 1 over 2, 3, that'd be 4 over 3, then 5 over 4, 6 over 5, okay, so on and so forth. And I'm kind of just doing this in my head. And is this going to be bounded? And I could plot these, but I think it's easier just to say, look, what two numbers do these always stay between? It looks like the biggest number we got here is a 2. This would be 1.5. This would be 1.33-ish, 1.25. So it looks like as big as we get is 2. And the smallest that we get, it looks like we're converging actually to 1, it looks like. Okay, so that's what I'm thinking in my head at least. So I think 1 and 2 are going to be bounds. Let's prove that that's the case. So a sub n, which is equal to n plus 1 over n, that's bigger than, I could subtract 1 from that numerator to get n over n, and that's 1. So a sub n is definitely always bigger than 1. Likewise, it's equal to n plus 1 over n, and that's less than or equal to, as long as n is sufficiently large, like say at least 2, then that's going to be smaller than just doubling the n. 2n over n. And of course I can cancel n's on top and bottom to get 2. And there's my proof that a sub n is trapped between 1 and 2. Since n is between 1 and 2, the sequence of ANs is bounded. Okay, take a look at another. So, is this going to be bounded? And again, I think it would help us to start by writing out the first few terms. And so I'm starting by plugging in 0, so I get 0 over whatever, 1 over negative 3, 2 over 9, then we've got 3 over negative 27. I won't simplify that just to make sure the pattern's obvious, because now I'm going to have a 4. It's going to be positive here, and then it's going to be 81, negative 5 over 243. Okay, and that's probably enough right there. So what do I got? Well, I've got a bunch of positives and negatives, but it's all fractions. It's small over big. It looks like I'm going to be bounded between -1 and +1. And sure, I can prove that. What I'll just do is, this is not a n though, it's bn in this problem. And now let's prove that this inequality exists. Bn, I'll do the bigger one first. Bn is equal to n over -3 to the n. And yeah, I can make this n bigger. If I replace that with just first of all, I can make this bigger by getting rid of all my negatives, actually. N over 3 to the n. And I could make it even bigger by making instead of n, I could raise 3 to the n power, and that would be bigger, wouldn't it? And then finally, that's, of course, the number 1. All right, likewise, the bn, which is n over -3 to the n, I can make that smaller by always having the negative, n over 3 to the n. I just pop out that negative so they're always negative. And then since I'm negative, by making the numerator bigger, I'm making a bigger negative number, say -3n over 3n, and that's -1. So there's a more rigorous proof of what was kind of obvious if we just wrote out the numbers, that the bn's are trapped between -1 and +1. So since we have a lower bound and an upper bound, the sequence of bn's is bounded. And again, if you want to see a picture of why that's the case, we can plot these numbers. Zero goes to 0, 1 goes to -1/3, 2 goes to 2/9, and then so on and so forth. And we can easily see from that picture that since we are always dealing with our fractions, it's bounded between 1 and -1. So this is definitely a bounded sequence that we're dealing with. Here's the proof of why. All right, so let's take a look at another definition. And this is what's called a monotonic sequence. A monotonic sequence has the property that it never increases or it never decreases. All right, and so there's two pictures of monotonic sequences. There's the picture of the monotonic sequence which never increases, and we call that, well, non-increasing. And from the picture, if it's not increasing, then it only has two things it can do. It has to either decrease or has to stay the same. And it can stay the same. It can stay the same forever, actually, as long as it never increases. The other option is that it never decreases, which is known as, well, non-decreasing. Let me spell that correctly here. Non-decreasing. And it's the same sort of picture. It's just that it's increasing or staying the same. So there's a non-increasing. And again, as long as it's always doing the same thing, basically. That's what I think of when I think of monotonic, is that the sequence keeps doing the same thing. It keeps going down or horizontal or down, or it keeps going up. Or again, it might be more appropriate to say it never goes up or it never goes down, depending on how you want to look at it. In any case, let's identify whether some sequences are monotonic or not. So we're back to this n plus 1 over n thing. We want to know whether it is monotonic. So again, we will take a look at the numbers first, perhaps, and that way we'll get a intuition for whether it's monotonic or not. So if we do the first few numbers, we get 2 over 1, 3 halves, 4 thirds, 5 fourths, 6 fifths. And if we look at the numbers, this is 2, 1.5, 1.3-ish, 1.25, 1.2. It looks like they're decreasing. In fact, it's never even staying the same. It's always decreasing. And so, yes, I think this is monotonic. The way I could prove this, if I want to do a rigorous proof, is I need to show that it's always getting smaller or the same. So a sub n plus 1, what would that equal? That'd equal n plus 2 over n plus 1. And then how can I rewrite that? I could rewrite that as, well, I want to get that as a fraction over n, so I can compare it with an. So if I want to do that, then I could take n and n on the top and bottom, n squared plus 2n, n squared plus n. Actually, we'll leave the bottom factored out. And then I want to be able to do some canceling here. So let's see here. I've got n plus 1 up here. I could add 1 and subtract 1 to complete the square. And that gets me n plus 1 squared minus 1 all over n plus 1 times n. That's equal to, I can split this up into n plus 1 squared over n plus 1 times n minus 1 over n plus 1 times n. Finally, I can cancel the square here and here. It gets me n plus 1 over n minus something positive, right? So I would make it bigger if I were to get rid of it altogether. And that is my an. I'm sorry, that would make it would make it bigger if I got rid of it. Pardon me. And that's an. So, right. So what happened here exactly? Well, the an is bigger than the an plus 1s, always. And these are the previous terms. And so that shows that an is greater than or equal to an plus 1. That means that things are always getting smaller or they're staying the same. And that shows that the sequence of ANs is monotonic. So again, there's the big old rigorous, algebra-y proof. But the intuition is perhaps even more important. Just being able to look at a sequence, plugging in a bunch of numbers, and seeing that it's always decreasing. It's always getting smaller and smaller, regardless of how much you liked this proof leading up to that fact. Being able to identify monotonic sequences just by looking at them is pretty important. Okay, and another. We'll go back to this example. Is this going to be a monotonic sequence? And I'm not sure it's going to be. Let's remember what the sequence looks like. If I were to plug in numbers starting with 0, I get 0, I get negative 1/3, I get 2/9, I get negative 3/27, 4/81. It's probably enough. And no, that's not going to be monotonic because either it needs to never decrease, but here it decreases, or it needs to never increase. But hey, negative to positive, that's an increase. So Bn from n equals 0 to infinity is not monotonic. Because 0 decreases, actually we'll write it like B0, which is 0, decreases to B1, and B1 increases to B2. So all I have to do is just show an example of some pair of terms where it decreases and another pair where it increases, and that will prevent monotonicity. Okay, so it seems kind of technical, right? We've got this idea of a bounded sequence, a monotonic sequence. Why would we care about naming these things and and talking about these properties? And that's where the monotonic sequence theorem comes in. So I'm just going to write this down real quick. The monotonic sequence theorem. And this is kind of the punchline for this whole chat here, because all of these sequences converge. That's all bounded, monotonic, so it has to have both properties, not just monotonic. Probably should have called it the bounded monotonic sequence theorem if you want it. But all bounded monotonic sequences converge. And the proof would require a rigorous notion of convergence, but I'd rather just draw the picture showing why that happens. Now remember, monotonic sequences come in two flavors. Either they're non-increasing, and the picture of that would be now it's bounded and monotonic and non-increasing. So let's draw the bounds. So it has some sort of bound, like so. And it's non-increasing. That means it's always decreasing or staying the same. So it starts here. It can stay the same if it wants. It can decrease. And the idea is that it doesn't have anywhere to go. We can't decrease on down forever because of this lower bound right here. We always have to stay above it. We could get really close to it, but we can never go below it. And we can't like wiggle around and prevent convergence because we're monotonic. We never can increase. So we have to always keep going down or staying the same. And we can see how that would have to converge to some number. It's not going to wiggle or go out to a negative infinity or positive infinity. And it's going to be the same sort of picture if it's not decreasing. And same sort of idea. We're going to have some bounds because we said it was a bounded monotonic sequence. And this sequence is not allowed to decrease, which means it has some value. Maybe this starts indexing at 1, I don't know. But for each of these tick marks, we can stay the same or we have to increase. We just can never decrease, and you can kind of tell that because we can't wiggle around and we can't go up towards positive infinity, this is going to have to converge somewhere. And that's the idea behind the rigorous proof. It's just these pictures right here. And so we will use this fact when we start introducing series, which we'll think of as a sort of sequence actually. And series involving positive terms are going to be bounded and monotonic. And that will help us show that they will converge, or they will be monotonic. And if they're also bounded, then we'll be able to say that they do converge.